Hi, today we're going to look at implicit differentiation. So this is for relations that cannot be written in the form of y equals f of x. So in other words, when we can't isolate for y on its own. Now these are called implicit equations. So for example, if we had x cubed minus 2xy plus y cubed equals 0, we're unable to isolate to get y on its own, so we can't change it in the form y equals f of x. So for something like this to differentiate, we have to use implicit differentiation. Now, to solve these, not all the time will we have everything on one side of the equation. Often we'll have stuff on both sides. So we want to differentiate both sides of the equation with respect to x. And then we're going to solve the resulting equation for our derivative of y. So we'll look at some examples. So first example is if x squared plus y squared equals 25, so that looks like the graph of a circle. We want to find the derivative of y with respect to x. So to get this, we're going to go d of dx of each side of our equation, so x squared plus y squared equals d over dx of 25. Now from earlier rules, we know we can break this up. So this is d over dx of x squared plus d over dx of y squared equals our derivative of 25, which we know is 0. Now, essentially, when it comes to this part here, we're going to use our chain rule. So when we have d over dx of x squared, but d over dx of y squared is d over dy times y squared of dy over dx. And I said times y squared here, but it's d over dy of y squared. Okay, our derivative of x squared is 2x. And then we have plus essentially our derivative of y squared, so that's going to give us 2y, because we're taking the derivative with respect to y, and then times dy over dx, so our derivative of y with respect to x, and we know that equals 0. Now, we want to find dy dx, so we just now need to rearrange to get this part on its own side. Subtract 2x from both sides of our equation. So that gives us 2y times our derivative of y with respect to x is equal to negative 2x. At this point, divide both sides by 2y. So that gives us our derivative of y with respect to x is equal to our 2's are going to cancel out, so negative x over y. Okay, next example, we want to find dy dx if 2x to the power 5 plus x to the power 4y plus y to the power 5 equals 36. So once again, we have a situation where we can't isolate for y, so therefore we will do implicit differentiation. So that means we're doing d of dx of 2x to the power 5 plus x to the power 4y plus y to the power 5 equals d over dx of 36. So now we'll use our rules to split this up. So this becomes d over dx of 2x to the power of 5 plus d over dx of x to the power of 4y plus d over dx of y to the power of 5 equals our derivative of 36, which is 0. Now, if we take the derivative of 2x to the power of 5, that's going to give us 10x to the power of 4. Now here we have essentially two functions multiplying by each other, so we have to use our product rule. So we'll take the derivative of our first term, so we've got plus dx of x to the power of 4, and then that's multiplied by y, plus our first term times the derivative of our second term, which is our y. And then we have plus our derivative of y to the power of 5. So what we can do is change this into d over dy of y to the power of 5 times dy over dx. Now we know that equals 0. So we've got 10x to the power of 4 plus 4x cubed times y plus x to the power of 4 times our derivative of y, or sorry, not, that times our derivative of y, which is just going to be dy dx, plus 5y to the power of 4 times dy over dx equals 0. So we want to find dy dx. It's in two terms, so I'd start by moving other terms to other side. So that gives us x to the power of 4 times dy over dx plus 5y to the power of 4 dy dx equals negative 10x to the power of 4 minus 4x cubed y. Now what we can do is both terms on this side have dy dx, so we can factor that out. That gives us x to the power of 4 plus 5y to the power of 4. And we'll leave this side as is for time being. Now to get dy over dx on its own, we'll divide both sides by this. So that gives us dy over dx equals negative 10x to the power of 4 minus 4x cubed y over x to the power of 4 plus 5y to the power of 4. So this would be our dy dx of this function. Okay, next example, we want to find y prime if x squared plus square root of y equals x squared y cubed plus 5. So once again, we'll do implicit differentiation. So we're taking d of dx of x squared plus the square root of y is equal to d over dx of x squared y cubed plus 5. We'll break these up, so that gives us d over dx of x squared plus d over dx of square root of y equals d over dx of x squared y cubed plus d over dx of 5. Now we know that our derivative of x squared is 2x. Now we'll take our derivative of the square root of y. So we know that's 1 over 2 root y. And then this is going to be times dy over dx. And that's equal to, we'll use our product rule here. So we'll take our derivative of x squared, so that's 2x times y cubed. And then we've got plus x squared times the derivative of y cubed, so times 3y squared times dy over dx. And then derivative of 5 will just be 0. Okay, so now that we've got to this step, I'm going to move the dy dx terms to one side, everything else to the other side. So I'd have 1 over 2 times the square root of y minus x squared. Actually, let's reorder the terms as we do this. So minus 3x squared y squared. And I just realized I forgot to include the dy dx here. So I've got 1 over 2 square root of y dy over dx minus 3x squared y squared dy over dx equals 2x y cubed minus 2x. Now we can factor out the dy dx, so we've got 1 over 2 square root of y minus 3x squared y squared in brackets and dy dx out in front. And that's equal to 2x y cubed minus 2x. And then we'll divide both sides by this. So that gives us dy over dx equals 2x y cubed minus 2x over 1 over 2 root y minus 3 x squared y squared. Now, often we don't like to have nested fractions, so I would multiply both the numerator and denominator for larger fraction by 2 root y. So that gives us dy over dx is equal to 2 root y times 2x y cubed minus 2x over, when we multiply this by this, that just gives us 1. And then negative 3 times 2 gives us negative 6 x squared. And then we've got y squared times y to a 1/2. So that would be y to the 5 over 2. Okay, next example. Find the slope of a tangent to a curve x squared plus x cubed y squared minus y cubed equals 13 at the point 1 comma negative 2. So first thing is we're going d over dx of both sides of our equation. So x squared plus x cubed y squared minus y cubed equals d over dx of 13. So essentially we've got d over dx of x squared plus d over dx of x cubed y squared minus d over dx of y cubed equals our derivative of 13, which is 0. So our derivative of x squared is 2x. And then we have our product rule occurring here. So that's 3x squared times y squared plus x cubed times 2y times dy over dx minus our derivative of this. So 3y squared times dy over dx. And we know that equals 0. So once again, I'll move the terms that don't have dy dx to the other side. So we've got x cubed, or 2x cubed y dy dx minus 3y squared dy dx equals negative 2x minus 3x squared y squared. We'll factor out the dy dx. So we've got dy over dx times 2x cubed y minus 3y squared equals negative 2x minus 3x squared y squared. And then getting dy dx on its own, we get negative 2x minus 3x squared y squared over 2x cubed y minus 3y squared. Now we want to find dy dx at 1, negative 2. So we can write that down as dy dx at 1, negative 2. So we've got negative 2 times 1 minus 3 times 1 squared times negative 2 squared over 2 times negative 1 cubed times negative 2 minus 3 times negative 2 squared. That gives us negative 14 over negative 16, which simplifies to 7 over 8.